All right, hope everybody's having a good day today. We are going to start with the difference quotient. We're going to go ahead and talk about this. I would strongly encourage a lot of people to go ahead and copy this down so that you have a point of reference. Okay, but before I go ahead and get into that, just a few items that are coming up this week and coming weeks. Remember, tomorrow, what's due? The inverse assignment, okay, that's due tomorrow. We'll talk about that, get it turned in. Then on Friday, you have an inverse quiz. All right. Okay, so hopefully you're looking ahead to that. If you have any questions, let me know. It's still a ways off, but on Monday the 14th, that's when we're going to have our first exam of the 6 weeks. That is just a couple of days before the PSAT. I want to go ahead and get it out of the way, and then we'll go ahead and take that 9 weeks assessment at the end of that one. Basically, it's a lost week. But I have also done something else this morning because several people are asking me about extra resources. Hello. Okay. William. There you go. People are usually asking me, can you post any additional resources or problems for specific concepts, a little extra practice before the quizzes and the tests. So what I've done, I've gone to connected.mcgrawhill.com. Let me go ahead and write this down. Connected.mcgrawhill.com. Okay, so I can go ahead and in this system put anybody's name in, and I can go ahead and assign you a digital copy of our textbook. It has everything that we're going to cover throughout the year. It has additional resources. I believe it even has video tutorials. So if that's something that you're interested in, let me know. I'll go ahead and put your name in the system. And then what you're going to need to do, go to this website. After I put your name in the system, if you go to the website before I put your name in, nothing's going to happen. But it's going to ask you for a username and a password. Both are capital LBB and then your 1000 number. Okay. Now you're going to need an internet connection, of course, to get to the website and to download the textbook. But once you have it downloaded to your phone, to your laptop, home computer, it is there for as long as you want it. Okay, so I think we're going to go ahead and do that instead of my posting occasionally those extra resources, because sometimes I just don't have time to go ahead and do that. So if anybody's interested in that, please let me know. I'll get your name in, and if you have any troubles, you can come see me. Okay, I think that's all I got. Let's talk about this difference quotient right here. So you'll notice I've already set up the first 3 blanks. The first blank, f of x plus h, well, what did we always do when we came to a problem like this? The first step was to replace every x with what? X plus h. Okay, so that's what I did. And then I expanded it, okay, like it said here. Then f of x is just the original function that we're attempting to find the derivative of. And now the third blank was just substitution. You were taking what you had from the previous 2 and plugging it in here. Now I need to start to manipulate this expression. Remember, I gave you several hints throughout the day on Friday. The one hint on your paper was you need to use a conjugate. What's a conjugate? What's that, sir? Not by 1. Okay, so a version of 1. Now that's coming up. We will have to multiply by a version of 1 using the conjugate. Okay, but we're still to the original question. What is a conjugate? Somebody give me a binomial. Any binomial expression. 2x plus 1. So if we have a binomial, 2x plus 1, its conjugate would be 2x minus 1. By definition, they're binomials that have identical first terms, but they have opposite last terms. The second terms are going to be opposites. So basically, if one's a positive, the other one will be negative. If I were to give you something like 5x minus 2, the conjugate would be 5x plus 2. So it's not a new concept. You've seen conjugates before. Okay, so looking at your numerator here, we have a radical binomial expression. So what we need to use is the conjugate. What would be the conjugate of that expression? There you go. We'd have the same 2 radicals, x squared plus 2xh plus h squared minus 1, and then plus the second radical, x squared minus 1. Now, Connor, what were you saying about a version of 1? There you go, because this isn't an equation, it's just an expression. It doesn't equal anything. So if I were to go ahead and say, like some people had on Friday, the idea to square it, that would be changing the original value. Okay, what I need to do is multiply by the conjugate, but in both the numerator and denominator. Okay, because if I multiply anything by 1, it stays the same. All right, so down here I'm going to have square root x squared plus 2xh plus h squared minus 1, and then plus square root x squared minus 1. Okay. Now, what's my next step? Since I have my conjugate and I'm multiplying by a version of 1. Sir? Oh, I wouldn't cross multiply. It's not an equation. How do I multiply fractions? Just straight across. So I've got two binomial radical expressions, which are conjugates, that I need to multiply. And remember, I provided you with an example right over there on how to do that. What's the acronym we use to multiply binomials? FOIL. Okay, so what's F stand for? First. So I'm going to multiply the first radical by the first radical. But you'll notice I'm multiplying the square root by itself. What's going to happen if I do that? Radicals will cancel each other out. You're going to basically be squaring a square root. So all that's going to be left is x squared plus 2xh plus h squared minus 1. Okay. Now, what does the O and the I stand for? Outside and inside. But why do I not need to worry about those? Because they're conjugates. When you multiply conjugates, the outside and the inside products will always become opposites. All right. And even if I were to go through this, just to kind of streamline it a little bit, make it go a little faster, let's just say this first radical is A, the second one's B. So A and B. If I were to multiply the outside, so I'm going to multiply the first radical by the last, so that would just be AB. If I were to then multiply the inside, I'm going to get AB as well, but you'll notice one is positive, one is negative. Conjugates, the opposite and the inside products are always going to cancel. So if we realize that, we don't even have to do anything there. Okay. Now what's the L stand for? The last. Okay, so I'm going to go ahead and multiply the last. So it's a negative times a positive, so that's going to end up being negative. But again, what happens when I multiply a radical by itself? What cancels? Yeah, the radical. So all I'm left with is the x squared minus 1. But remember, I'm subtracting that. And this is all over h times that binomial. The square root x squared plus 2xh plus h squared minus 1. And then we have our plus square root x squared minus 1. Okay. So just like I said the other day, you got to get those expressions, the terms, out of the radicals so that we can now simplify. If I distribute my negative by dropping the parentheses, that means we have a negative x squared plus 1. And just like every other difference quotient example we did, what happens? Well, you can cancel opposites. In fact, x squareds are gone. What else? The 1s are gone. Okay. Now what? Philip? Factor out the h. So 2xh plus h squared, if I pretend h is a greatest common factor, that would leave me 2x plus h, and this is all over h times that binomial. So x squared plus 2xh plus h squared minus 1, and then plus square root x squared minus 1. Now, why would I factor out the h's? What would that allow me to do? I can now cancel that h in the denominator. Okay. Now, at this point, I cannot simplify any further, so what do I do? Okay, what's that, sir? Yes, because we do that by taking the, starts with L. The limit as h approaches 0. Okay, remember, they even said, don't forget to take the limit as h approaches 0. So any h remaining just disappears. 0, 0, 0. So let's see, what's left in my numerator? 2x over. Now, if this radical loses 2xh and h squared, all he has left is x squared minus 1 plus the square root of x squared minus 1. Okay, but what can you do in the denominator? We can't cancel them out. They're what's known as like radical expressions. You can add or subtract radicals if two things are in place. They have the same. Okay, what's that? Okay, well, we don't call it an exponent. It starts with I. We call it an index, but you're correct. And we have the same, what do we call the expression below the radical? The radicand. So they're both square roots. They both have x squared minus 1. So it's the same. If I had x plus x, that would give me what? 2x. So if I have square root of x squared minus 1 plus the square root of x squared minus 1, that would be 2 over x squared minus 1. And then we have this 2x here. And then my final step would be just to simplify anything remaining. So there we go. That would be the derivative. Okay. Now, I want to talk to you about this for a second because from my observations and the papers I were looking at, I didn't see a whole lot of people trying. In fact, that's why a lot of people lost points on that paper. Okay. It looks to me like maybe one or two people knew about what's called the chain rule, knew immediately how to find the derivative, and then a lot of other people just copied it. Because I was checking, and very few people had work that actually gave me that expression right there. Okay. And I was thinking about that the other day, as I started putting the grades into the computer, I really wasn't getting the sense that people truly understood how that answer was found. And I didn't feel right giving a passing grade to somebody whose work didn't match up. Okay. So that's why those grades are the way they are. But I want to go ahead and kind of comment on this for just a second. Thanks, sir. Okay. Forget about the fact that this is a derivative. If you don't understand what that means, forget about the big picture. Okay. Look at what we did here. Okay. How did I simplify this expression? What did I use? Or let me rephrase. Is there any skill that we used here that we hadn't seen previously or you hadn't been taught previously? Yeah, it's just algebra. Okay. Forget about the big picture. It's just algebra. Okay. Right. I want to encourage you guys, you've got to try. Okay. You are going to see problems in here that I have not directly shown you how to work. Okay. And that's kind of the whole point. If I only go ahead and give you problems of types that I've already worked with you in class, then I don't feel you're going to be leaving here actually benefiting from it. You're not going to be growing. You're not going to be learning. Kind of think about, as you progress into calculus. Okay. There are going to be problems that you're going to come across that I will have not shown you. So what do we try to do to make that happen? Okay. Well, we try to help you become problem solvers. Okay. When you come across something like this, okay, I've never seen one like this before. I've seen one similar to it, but what do I know that I can apply to this problem? That's the kind of process we need to be thinking of. Okay. Unfortunately nowadays, and this is just my own personal observation again, it seems to me like failure has become a dirty word, and it's really not. Okay, it's really not. You can't be afraid to fail. I mean, Lord knows how many times have I stood up here and made a mistake. It's going to happen. Okay, we're humans. Okay. But you can't let the fact that you might make a mistake or you might fail prevent you from just trying it. Is everybody kind of understanding what I'm saying? Okay. I want to help you guys out. I want everybody to succeed. I mean, I do, but I don't want to hold your hand. Okay. You guys are very capable of doing this, and I will never give you a problem that you should not be able to solve. Okay, does everybody understand what I'm trying to say? Okay, all right. Now, retakes you have until Monday morning if you want to come on in. It's going to be a very similar problem to what we did here. Okay, right, so you still have a little bit of time. I wanted to go ahead and go over that before we did anything else. Now, while we're having our heart-to-heart and the tender music is playing in the background. I'll get to you in a minute. Okay. One other thing I felt is a good idea to go ahead and bring up today. Let's talk about the website for just a quick second. Okay. Again, I'm noticing something that is kind of disturbing to me. I'm kind of getting the impression that, again, people are not going to the website because people who were absent, they keep coming up to me, what did I miss? Where are my copies? And in fact, it's becoming even more increasing lately that students are getting upset with me because they're not going to the website. Okay, now that is a completely different discussion. But I really want to emphasize to you guys, the website is there to help you. Okay, it's there for the specific reason if you're not in class. I realize the video is not the same as sitting in class. It's better than nothing. Okay? I think a lot of people have gotten to this level and maybe we really don't know how to study. Okay? The ideal way would be you go to the website. If you're able to look at the video, fine. You don't have to look at the entire video, but look at the notes. At least look them over and see if you can get an idea, but come in with questions. If you come in and just say, I haven't visited the website, I got 5 minutes. I need you to teach me everything I've missed in the past couple of days. It's not going to happen. In fact, that's what happened this morning. The student got mad because we only had 10 minutes left in class, and he wanted me to cover every bit of material on the lesson we started yesterday. And I tried to explain that's not possible. That's not going to happen because if I could do it in 10 minutes, we'd already be done with this thing. Okay. So please, if you're absent, take advantage of that website. That's why it's there. Okay. Any questions on that? Any questions on the difference quotient? Now, Galen, what's your question? I'm not going to worry about this time. Okay. But starting with the composition quiz, the inverses quiz, we need to have the homework done. That's another issue, we've already talked about as well. Okay. I will admit I am getting more homework now that I've started the point bank. I'm really proud of you guys, but we can do better. Okay. I am not trying to take up your time. I know that you have way more important things you would like to do than math. Okay. Even I want to do that sometimes. Like when I go home, I want to spend time with my kids. Okay. I'm not constantly thinking about quadratics and derivatives and all that. Okay. I'm not the amazingly cool nerd you guys think I am. A little bit too quiet when I said that. Okay. But, there is a reason. You got to practice. The homework gets you ready for the quizzes, which in turn gets you ready for the exams. Yeah. And remember this year, I heard from a lot of other people in departments that there are a lot of failures the first 6 weeks because people are getting killed with only taking, quiz grades and the 2 tests. Okay, so please, if you're having trouble, let me help you. Philip. Door opens at 7:45. Oh, you can't come after school. There are no after-school tutorials. I've said that several times. Okay, sorry for the inconvenience, but unless I happen to be staying and you happen to see the door is open, nope. Okay. Anything else? Okay. All right, well, how much time do we got? 41. We got here at 52. We got plenty of time to at least go a little further on our notes. And we should be able to wrap this up tomorrow. But we'll get as far as we can. Okay. So we started our trigonometry unit yesterday. We had several vocabulary words. We talked about initial and the terminal side. The initial is where you begin to rotate. The terminal is where you stop rotating. And the direction you rotate is very important. If you rotate counterclockwise, that's a positive angle. If you rotate clockwise, that's a negative angle. And then we had coterminal angles. Okay, now these are angles that have different measures, but the same terminal side. So you can rotate positively counterclockwise, negatively clockwise. As long as you stop in the same position, they're what we refer to as coterminal. And then we spent some time talking about reference angles. Okay. Reference angles are always created using the terminal side wherever it stops and the closest what? Closest x-axis. Okay, so we went through several examples. And how far did we get on this? So did we get the degrees, minutes, seconds?
Yes.
So we did get both of those. Cool, cool, cool. And again, maybe even tomorrow, if anybody's interested, wants to know how to do those by hand, let me know. I'll go ahead and show you. Right now, I was just interested in showing you on the calculator. Did we talk about radians?
Yes.
We did. Okay. So radians. Let me go ahead and fill this back in. 1 revolution in radians was 2 pi. Were there any questions on how we find 1 radian? Like how we classify that? Or did somebody tell me what we talked about yesterday? Like how do you find that 1 radian, the 57.296 degrees? Okay, Andrew.
I kind of didn't grasp it, but
Okay.
you were explaining it with the distance, same distance of...
So I did talk about my hands.
Yes.
Okay. So what was I doing with my hands?
I have no idea. I just...
2 circles?
Yeah.
Okay. Well, not 2 circles, 2 radii. Okay. All right. Yes.
The radius of the circle, if you go that distance on the outside of the circle,
That's exactly right. So Connor is correct. Let's say I have the radius of a circle, and this works for any size circle you have. If you take the length of the radius, whatever that length is, okay, if you then find that length along the outer edge of the circle, okay, starting from the positive x-axis, so that this length right here is the same as this arc length right there. They're both the same distance. Now, wherever it stops, the angle created, that is 1 radian. Now, what I was talking about yesterday, I was trying to visualize this. Imagine that my hand here is a radius. My wrist is the center of the circle, and the tip of my finger is touching the circle, so it goes around like that. So if I were to place my other hand on top, hopefully they're going to be the same length. Okay. So if I take that same length of the radius and I apply it to the outer edge of the circle, okay, 2 distances that are the same. The angle created between them, that's 1 radian. Okay. All right. And we're going to be doing a lot with radians. How far did we even do this?
No.
Okay. So let's go ahead and start with this right here. Now, if you're going to go ahead and look at the unit circle in radians, you're still going to start at the positive x-axis, which, what did we call that yesterday? 2 words? Starts with an S and then a P? Standard position. Okay. So you start with 0 radians. We said that 1 full revolution was 2 pi radians. So let's kind of fill in the rest just like we did with the degrees. What's half of 2 pi? Pi. So half a rotation is pi radians. What's half of that? Okay, 1/2 pi. So we'll say pi over 2. Now what's 3/4 of a revolution? 3 pi over 2, or 3/2 pi. Okay, there we go. So one of the most crucial items is being able to tell where your terminal side is going to stop. Now for degrees, people really don't seem to have a lot of issues with that because the number is right in front of you and it's usually very easy. But with radians, it can get a little tricky for some folks. Now before I go ahead and show you some of those examples, okay, we use a central angle of a unit circle shown at right, that's not left, where the vertex is the center of the circle. 1 radian is the measure of the central angle that subtends or intercepts an arc equal in length to the radius of the circle. And that's just another way of describing what I was telling you a moment ago. Okay, now, what's the formula for the circumference of a circle? It's 2 pi r. Now, we also use pi d, but because we're defining the radian in terms of a radius, we're going to go ahead and use 2 pi r. Okay, 2 pi times r. Well, r is the radius, so the circumference of a unit circle, if the radius is 1, we're just going to have 2 pi times 1 units. So that's why 1 full revolution is considered 2 pi radians. Okay, because remember, the circumference is basically the distance around the circle itself. Okay. Now, if theta is a central angle in a circle of radius r, and if theta is measured in radians, then the length s of the intercepted arc is given by s equals r theta. That's actually really important, but it's in an upcoming lesson where we're going to look at that. You guys remember arc length and area of a sector? We are going to be revisiting that, but we're going to be solving those using radians. Okay. So let's look at a few of these. Common radian measures. So what we want to go ahead and do is draw where the terminal side would stop after rotating this radian measure. Now you'll notice the first one's what? It's negative, so what's that tell me? I got to rotate clockwise. So you're going to see the same measures that we had here, but they're just going to be going in the opposite direction. So this would be 0, negative pi over 2, negative pi, negative 3 pi over 2, and then negative 2 pi. Okay. So what I always try to encourage people to do is think about the coefficient that pi has. All right, especially if your radian's in pi, which is typically a lot of what we're going to be doing most of the time. I want to go ahead and show negative 1/4 pi. Well, think about it. What quadrant would that be in? Okay, I heard 4. I heard, what'd you say, Will?
No, never mind.
Okay, changed his mind.
4.
Okay, 4. I heard 3. Okay, well, think about that negative 1/4. Okay, is negative 1/4 larger or smaller than negative 1/2?
Smaller. Oh,
It's larger. Remember, with the negatives, the larger the value looks, the smaller it actually is. So negative 1/4 is actually larger than negative 1/2, so it is going to put him right here. That'd be negative pi over 4. Okay. All right. Let's try the other two. Pi over 2 and pi radians. But do you notice anything about those? Where would pi over 2 be? There you go. In fact, both of these would be on an axis. See, there's pi radians, there's pi over 2 radians. If your terminal side stops on an axis, it doesn't matter where, that has a specific name. We call that a quadrantal. We call that a quadrantal. Well, this will be our last idea today before we go ahead and shut it down. You remember yesterday we were talking about reference angles? It's the angle created between the terminal side and the closest what? X-axis. Well, can anybody tell me if I have pi over 2, what's the reference angle? It would be 90 degrees. Here, it's the same distance from either the positive or the negative x-axis. Doesn't matter. Okay, so the reference angle here would be 90 degrees. Okay. Now, what's the reference angle here if it's pi? It would be 0. You'll notice the terminal side and the x-axis are the exact same here. So there's no angle existing between them. It would be 0 degrees or 0 radians, depending on what you wanted to look at. Okay, so just remind me, we finished up here, and we should be able to wrap this up pretty quickly tomorrow after our focus activity. Okay.